So we have three isotopes. Okay, we have three isotopes. We have hydrogen, beryllium, and carbon. And so what do we mean by an isotope? So the term iso, or the prefix iso, you've heard of it like in your biology class, all right? So like if something is, so you've heard of hypertonic, hypotonic, isotonic. And so remember hyper and hypotonic, so you had more water moving in or out of a cell, so the cell kind of shrunk or it increased depending on how much water was moving in or out. And then you had a state that was called an isotonic state for the cell, where everything was sort of balanced on both sides. It was basically the same on both sides. In math class, you talk about isosceles triangle, right? And so you've got two sides that are the same, right? So iso. So iso kind of meaning the same or equal. So right here we've got an isotope. What this refers to is we have something that is the same about the atoms, okay? So in this case, by saying isotopes of hydrogen, beryllium, or carbon, what we're saying is the isotope is just the term that is used to refer to the atom itself. Because there's multiple forms of hydrogen, there's multiple forms of carbon, etc., etc., etc. They're all carbon, they're all hydrogen, because there's something about them that is the exact same. But when there are things that are different, what we do is we call it an isotope of that atom. So we'll say a hydrogen isotope, or we'll say a carbon isotope. All right? And so we're going to practice at least getting the basics of isotopes out here. And so to do this, we obviously need our periodic table. We've already used our periodic table to get this going before, so we've got hydrogen. So the first thing we need to do is to take a look at our trends that we were looking at with hydrogen. So let's come back here to our periodic table. So remember, we see hydrogen is there in group 1, period 1. So the thing to know is that if something is in period 1, there will be one sort of volume of space where electrons can go. So every time you go to a new period, you go out further from the nucleus where electrons can be. And so we know electrons have a negative charge, and so all of these elements are not magnetic, but you understand the concept of magnets from grade school, from elementary school. If we know electrons are negative, if you take two negative sides of a magnet and you try to get them close to each other, there comes a point where they start to repel each other, right? And they'll repel, they'll push each other away. But if you had positive, negative, then of course opposites they would attract. But the two like charges, as they get closer and closer and closer, you feel that pressure, right? That push for them to go away. Well, if we think of atoms, then what's happening with our atoms is the same thing. As those electrons get closer and closer to each other around the atom, as we go down the period on the periodic table, as we increase the amount of spaces that are available around where electrons can be around the nucleus of an atom, then that means as there's more electrons packed together, they are repelling and pushing each other further apart to some amount of equal spacing. And so the periods represent the region of space, of three-dimensional space, where electrons can be found. So right here we've got hydrogen 1. We've got hydrogen, right? And hydrogen, you can see, is in group 1, period 1. So what we do is we go back to our problem, and we need something that represents our nucleus, right? So we've got hydrogen, all right? I'm going to draw a nucleus. I'm just going to say that represents my nucleus, all right? Let me make this a little bit larger. There's my nucleus. All right, there's my nucleus. And your nucleus has protons and it has neutrons. So protons, how many are there? Neutrons, how many are there? Well, we're doing hydrogen first, right? The thing we're worrying about first is hydrogen. So let's go back to our periodic table. Here's hydrogen. Let's zoom in on hydrogen. That 1 right there at the top, if we look at our legend, is the atomic number. The atomic and the bottom number is our atomic weight or our mass number, and it is an average number. Okay. And that has everything to do with the fact that there's multiple forms of an atom. And so think about your class. If you're taking a class and you have multiple grades, you can get an average. You've got several different grades. They're all grades, but because they're different, you got some average of all those grades, right? So right here, hydrogen, group 1, period 1, right? And so we can see that it has an atomic number of 1. And the mass number is also 1. So go back. Our atomic number is 1. Atomic number is the number of protons. The total mass number is also 1. Now it said 1.008, which is essentially a value of 1. It rounds down to 1. What you need to know is that mass of an atom, the majority of the mass of an atom is in the nucleus. And that's this circle that we have here basically represents our nucleus. Electrons have mass, but that mass is negligible. It is really, really small. So think about it this way. If you were to stand on a scale and the scale says 100, and then all of a sudden I place a feather in your hand, the scale doesn't change. It doesn't suddenly say 101. It doesn't even say 100.1 because we know the feather is so light that that scale can't pick it up. The feather has mass because it's made of matter. It's made of atoms, but it's so light. It has so little mass that the instrument that we're using to measure it can't pick it up, right? So knowing that, all of the mass resides in the nucleus of this atom. All right, so that means that there are 0 neutrons here because 1 plus 0 is 1. So now we have a total mass number. So whatever we write into the nucleus has to add up to the total mass number. And for hydrogen, from the periodic table, we saw that was basically 1. All right. The next thing we need to look at is hydrogen has 1 proton, and protons have a positive value. Okay. What we want to do when we draw out our atom, an atom by definition has a neutral charge. It has a total charge of 0. So if we go back to this right here, we saw that hydrogen was in period 1, and we stated earlier that if you're in period 1, that represents one sort of orbital, one sort of ring, one sort of region of space around the nucleus. And so we typically just sort of draw a circle around the nucleus to represent an orbital. Okay, and so there's that one orbital. So this orbital right here, we would just say, right here. So we would say n equals 1. So there's just one orbital right there. Okay, that's the first orbital. So I'll just call it that. I'll just call it the first orbital, the first energy level, the first orbital. All right, first energy level. Those are the basic terms that are used. So if we know that protons are positive and electrons are negative, and we need an atom to have a total charge of 0, then that means that there must be just one electron somewhere on that orbital, anywhere. Now I put that there. I could have put it over here. I could have put it up here. It doesn't matter where you put it. Just somewhere on that orbital. Typically we kind of put it either to the sides or the top or the bottom. All right. So that's it. So there's hydrogen. So here's hydrogen right here. And we want to do it with proper notation. So notation means the first thing we do is we write the element symbol, hydrogen, H, capital H. And then there's 2 numbers that we need. We need the atomic mass and the atomic number. So the atomic mass for hydrogen, we said hydrogen has a mass of 1. That goes on the top left as a superscript. And then we have the atomic number, which is the number of protons. There's also just 1. We put that as a subscript on the opposite side, on the left side, okay? And this right here represents the notation. That right there is the notation. And we tend to call this isotope notation. Right? This is the isotope notation for this element. So now you know that whenever we write the isotope notation for any element, we have to have the symbol, the element symbol, we have to have the atomic mass, and then the atomic number. Okay? And that gives us some valuable information. Let's think about this. We know we have 1 over 1, right? Well, let's go back to a basic math, what we learned in grade school. Well, what's 1 minus 1? 0. So it's set up like column math. And if you look over here, we have 0 neutrons. And so that's part of the reason for setting it up that way, is it makes it easy to very quickly, when you look at the isotope notation, in a snap, you can figure out how many neutrons are there. All you do is take the difference of the two numbers. You got the mass number minus the atomic number, and you have the number of protons. All right? So, I don't know, let's take a look at beryllium. All right, so let's look at beryllium. So beryllium, let's go back to our periodic table, and we find beryllium. There's beryllium on the periodic table. All right, and you see that it has a 4 up at the top. So remember, the 4 represents our atomic number of protons, and then we see that we have a mass of 9.012. That's going to round down to basically 9. So we have a mass of 9, and we have atomic number of 4, right? So let's go back to our problem. So atomic number of 4. Oh, probably help if I had the pencil. I had the pen. So we have an atomic number of 4. And we saw that beryllium, Be, it had a mass of 9 and an atomic number of 4. 9 minus 4 is 5, so that's how we know we need 5 neutrons. And that's what our nucleus for beryllium is 4 protons, 5 neutrons. All right. Now let's go back to beryllium, and we see that beryllium is in period 2. Remember, periods go left to right, right? They're going across, right? So it's in period 2, so that means it has a total of 2 orbitals around it. So we go back. All right. Let's use our fancy tool here. Let me go ahead and keep that black for you. So we've got 1 orbital, 2 orbitals. All right. I'll try to draw it a little more centered for you. And that'll work. All right. So now, here's where, using our periodic trends, here's where the magic unfolds. Watch this. So we have 4 protons. So we ask ourselves, if we want our atom to be neutral, in other words, have no charge, and we know protons are positive, that means we have 4 parts that are positive, so we can just say positive 4, right? Well, positive 4 plus what would equal 0? So how many electrons do we need? We need 4. We would need 4 electrons, and since we know electrons have a negative charge, 4 plus a negative 4 is the same as 4 minus 4, gives us 0. All right? So now we go back to our periodic table, and here's where I want to show you how to use your trends. We said going left to right that there are trends that you can see. So if you look where hydrogen is, starting with hydrogen, what I would like you to do is think of every single block on the periodic table. Think of every single block on the periodic table as being a space where an electron can go. Okay, so there's an electron can fit in a space around the nucleus where the block for hydrogen is. There's another electron that can fit where helium, the block for helium is. Another where that third electron, you see there's a 3 there for lithium, and then a 4th right there with beryllium. So that's 4 electrons, and we need 4. So 1, 2, 3, 4 gets us to beryllium. So that makes sense. 4 plus 4 is 0. 4 plus a negative 4 is 0. But notice that there's only 2 spaces in period 1. Hydrogen all the way to helium. There's only 2 spaces. So we go back, and I'm going to put an electron there, and now I've put 2 electrons in that first orbital, right? And then notice that we had 2 spaces in the second orbital. First orbital was full, we go down to the second orbital, we fill lithium, and then we fill beryllium. So that means go to the second orbital. Now I have a total of 4 electrons. 2 of those electrons are on the first orbital, and 2 are on the second orbital. All right? There's our first orbital. And then there's our second orbital. And actually, I want to write it this way instead. Let me back that up. I want to write it this way instead. So there's our first orbital, and here's our second orbital. So now you might be asking, he wrote the same words, why did he bother to take his time to replace that? I'm trying to give you a visual for a later lesson where the first orbital is, then we get to the second orbital. There is this concept that as we get further and further away from the nucleus, there is an increase in the amount of energy around that atom that is trying to bind and hold all those electrons in those regions of space. And as more electrons get packed in there, there's more negative particles that are trying to repel and push each other away, but at the same time, there's something happening that is bringing those closer to the nucleus. So there's an exchange of energy. And so, as a rule of thumb, a higher amount of energy levels, higher amount of energy is what it usually sort of translates to. Okay. So now that we've looked at hydrogen and beryllium, let's go with something a little bit different. Let's go with carbon. Carbon, talk about it in biology all the time, and carbon is essential to life, so it makes sense for us to understand carbon. And there's an entire field of chemistry dedicated to just understanding carbon and what carbon does, organic chemistry. And it's studied in inorganic chemistry as well, but essentially the study of organic chemistry, chemistry of life, essentially, has everything to do with this atom right here. So this is the basics, the foundation that builds every single thing that's alive on this planet. Every known thing that we know in this universe has everything to do with this atom and how it's structured, why it's structured, and how things bond to it, how things don't bond to it, why they do, why they don't. So let's just jump in. So we've got a proton and a neutron. For our isotope notation, we're going to need to put our element symbol. Well, we know carbon is a capital C. That's easy enough, right? So now let's go back to our periodic table, and we zoom in and we see right there that carbon, it has protons that have a 6, right? That's the atomic number 6. And 12.011, that is the mass number. Again, that's an average mass number because there's multiple isotopes. Not that what's on the periodic table is like the most stable, most common form of whatever element we're looking at. So the most common stable form of isotope of carbon is this carbon-12, and that's how we say it. We say the element name and then the mass number. So this is carbon-12. 0.011 is going to round down to basically 12, right? So, and then atomic number 6. So we go back, and we realize that there are 6 protons, and the mass is 12. So the mass is 12, and there are 6 protons. 12 minus 6 tells us there's 6 neutrons. All right, and again, we're going to need the same number of electrons that we have that equal the number of protons we have in the nucleus. Since the positive particles in the nucleus, the protons, we have 6 of those, then we would need 6 electrons for it to equal 0, because 6 plus a negative 6 would give us our 0, right? So we go back to carbon, and we see that carbon is in period 2. Remember, that's 2 orbitals, so there's going to be 1 orbital ring around the nucleus and then a second around that one right there. And so now let's take a look. If you look at the periodic table, remember we said where every block is for right now, we can think of it this way, a concept where there's the space where 1 electron can fit around that 3-dimensional space around the nucleus of the atom. Okay? So that means there's 1 electron where the hydrogen element is at. There's a second one where helium is. So we're at the end of that period. We have to drop down, go back to the beginning. We see that we're there at lithium, beryllium. Then we go over boron, and the sixth one gets us right where carbon is, and we need 6 electrons. We need 6 electrons. All right. So that gives it that. So you can see that on that first period, there's 2 spaces, 2 electrons, and then there would have to be 1, 2, 3, 4 on the second orbital. 4 plus 2 is 6. So let's go back to what we're drawing here. We've got our first orbital, and then we have our second orbital. Hey, that one's not too bad, actually. This little snap feature, this geometric shape feature on GoodNotes, it's a wonderful feature. I absolutely love it. So let's go with a different color so we can have some contrast. We said we needed 1, 2 on the first orbital, and you only ever can have 2 electrons on the first orbital. All right, it's easy math. So 1, 2, all right, and then we need a total of 4, right? So that's 1, 2. So we need 1, 2, 3, 4. So we've got a total of 6 there. We are good to go. So on the, oh, I'm sorry, that's why it's doing that, because I still have the geometric shape on. So on the first orbital, all right, we see that there is a total of 2 electrons. And then on this second orbital, we see that there are 4 electrons. 4 plus 2, that's our 6. We're done. We're good to go. So now we have this is our stable carbon-12 isotope. All right. Hope that helped. Take a look at the other videos. We're going to expand this concept a little into much broader terms, but with more specific detail, so that we can use this for some other things. It's good seeing you again. Take care. 3 easy examples. You can see that I just picked 3 random atoms, and that what we're learning in this lesson holds true pretty much for the majority of these atoms, and to some degree all the atoms. But remember, and for note, where the transition metals begin. So after atomic number 20, things begin to change as far as how atoms are structured. Fundamentally, it's still very similar, but there's a lot more that we need to know. And again, these Bohr models, they are not true representations of a 3-dimensional atom. So everything is 3-dimensional. The coffee that I'm drinking, your fingernails, your hair, everything, the air you're breathing, it's all 3-dimensional. We draw those flat 2-dimensional objects so that we can have some sort of concept of where things are in association with something else. There's a center, so-called center, but that center has 3 dimensions. You can go all the way around it, and things are not just moving in a flat 2-dimensional circular or sort of circular motion. It has 3 dimensions in multiple ways, and so you have to sort of think beyond that. Think beyond just X and Y. You need to go back to what we learned in math class as well, and our math teachers introduced a third axis, a z-axis, and that helps us understand 3 dimensions. It helps us understand that we have something in an x, in a y, and we have something in a z. So if I do x this way, y this way, then I'm coming right at you for the z-axis, because there's our 3rd dimension, and that's what makes things spherical, square, rectangular, whatever the case may be. Everything has multiple sides to it, and the more geometric it is, then the more mathematical, there's mathematical equations for that geometry. But if not, there's other ways of doing that. But you just have to keep in mind that it's all related. All of this is related. Just a bunch of atoms that are sort of pushed and kind of held next to each other depending on temperature. So in previous lessons we've talked about phases of matter, which has everything to do with the type of substance that it is, how much energy is in the system, which means how much heat is nearby, how much heat has been absorbed by that matter itself, by that mass of matter, right? So keep all that in mind, but every time we do that, no matter what it is, it has everything to do with what you learned on the periodic table, all right? Hope that helped. I'll have plenty more lessons for you, plenty more examples. You should practice. pick a few of those. Anything that we haven't done all the way through atomic number 20 will follow these rules. Anything past atomic number 20 is for a much later lesson in chemistry, because when we get into those suborbitals, there's other dynamics that we have to understand, and so that's for a different lesson right now. But everything that we've talked about in this lesson, it'll work through atomic number 20, calcium. Good luck. Stay curious. It's always good to see you, and I'll talk with you soon.